To understand the complex nature of electromagnetism, we must first begin with a single, isolated positive charge suspended in a perfect vacuum. Gauss's law for electricity dictates that this stationary charge creates a radial electric field. It defines the fixed geometric rules for the space surrounding the particle. Because the charge is stationary, the field remains constant. Mathematically, the partial derivative of this field with respect to time is exactly zero. This static field contains potential energy, but it lacks the mechanism to propagate that energy outward. The system is essentially locked. This electric field is localized. It exists as a direct extension of the source charge, unable to exist independently of its origin. Moving the charge at a constant velocity transforms the entire system into a steady, unvarying, continuous direct current. Ampere's law for magnetostatics reveals that this steady current generates a secondary field, the magnetic field. The topologies of these two fields are distinct. While the electric field radiates from the charge, the magnetic field forms closed, cylindrical loops perpendicular to the vector of motion. Despite occupying the same space, these two fields do not interact under constant velocity conditions. The electricity and magnetism remain completely independent. Under static conditions, these fields are decoupled. They are physically incapable of detaching from the charge to cross a vacuum. In this state, the fields can only exert force on physical matter that enters their localized vicinity. This interface demonstrates the Lorentz force. We see an electron's curved path dictated by unvarying parameters for the electric and magnetic fields. The fields act on the passing particle, but they do not travel, confining energy transfer to the immediate geometry of this spatial grid. Neither Gauss's law nor Ampere's static law contains the mathematical architecture required to project a wave through empty space. To build a structure that crosses the vast universe, we must break the zero-time derivative condition by introducing a rapid temporal disturbance. The generation of an electromagnetic wave requires acceleration. We achieve this by oscillating the charge harmonically along an axis. Information regarding the charge's changing position is restricted by the speed of light. It cannot reach distant points instantly. This delay creates a topological kink in the electric field lines propagating outward from the source. Because of this propagation, the electric field at any distant point now varies over time. Mechanical acceleration translates to time variance in the vacuum. This time variance activates Faraday's law of induction. Faraday's law dictates that a time-varying magnetic field induces a spatially curling electric field. James Clerk Maxwell expanded on this relationship by identifying a symmetrical effect. He calculated the displacement current, proving that a time-varying electric field must similarly induce a curling magnetic field. These equations interlock. A changing electric field generates a magnetic field, which itself changes and generates a new electric field. Maxwell's equations describe a self-sustaining feedback loop, an engine that builds its own path through space. We see this engine ignite in an antenna, where alternating current drives charges in constant oscillation. This diagram shows the spatial relationship at the source. The current generates the encircling magnetic field vectors, while the separated charges generate the vertical electric field vectors. The outward pointing vectors indicate the energy flux is no longer localized. It's pushed away from the antenna. As the current reverses, the fields reverse, pushing the previous loops of electromagnetic energy into the vacuum. The physical antenna provides the initial input, but the mechanism of travel is the mathematical coupling of the fields. In empty space, we can examine the behavior of these fields isolated from their source charges. Taking the spatial derivative of Faraday's law links it directly to the Ampere-Maxwell law. Substituting the magnetic field with the electric field's time derivative isolates the electric field on both sides. This collapse results in the three-dimensional wave equation. This mathematical format dictates that the field must propagate through space to satisfy its own time-varying state. The electromagnetic wave exists because the vector calculus of the fields allows no other stable solution in a dynamic vacuum. Within the wave equation, a single coefficient sits before the second-order time derivative, mu naught times epsilon naught. In wave mechanics, this coefficient defines the inverse square of the wave's velocity. Epsilon naught represents vacuum permittivity, or the resistance to electric fields. while mu0 represents vacuum permeability, the resistance to magnetic fields. Evaluating the inverse of the square root of their product results in exactly 3 × 10⁸ meters per second. The speed of light is a constant derived from the electromagnetic resistance of the vacuum. Far from its source, the wave maintains a stable architecture as it travels. The electric and magnetic fields oscillate in phase, reaching their maxima and minima simultaneously. The vectors are perpendicular to each other and to the direction of propagation, identifying this as a transverse wave. Because these changing fields serve as their own continuous sources, they require no physical medium for transport. The mechanical acceleration of a microscopic charge translates into an independent structure of energy, propagating indefinitely through the vacuum.